Okay. You got a real axis and an imaginary axis. So that the complex number using A and B again, but that's standard notation. I haven't even looked to see what your text tells you, but I think A and B are pretty standard. A for the real part, B for the imaginary part, okay? Other notations are possible and necessary in many applications, but this means that like if A is here and B is here, here's a representation of C. Well, that was hard, was it? Okay. Now, let me ask, have you started Taylor series yet? It's unfortunate. Guess something I could say about the fuller representation of this thing. That's okay. You're going to do it soon because there aren't that many weeks left in the semester. Okay. So, okay, you got Z equals A plus BI. You got an angle. Okay. Which basically be arctangent of B over A. Okay. And I don't know why I said pi over 2 plus pi. I was debating about writing it in radians versus degrees. But this is math. There are no such thing as degrees. Unless you're talking about triangles. Okay. Okay. This just says that you know the inverse tangent always gives you a number between 0 and pi, or between 0 and 180 degrees if you're in degree mode. Okay. But I'm sorry. The inverse tangent always gives you a number between negative pi over 2 and pi over 2. Okay. If you're over on this side, you got to add 180 degrees or pi radians to that. Okay. Because the inverse tangent of this B over A would give you an angle down here. Negative angle. Okay, well, that you've got the angle. And the modulus. So just Pythagorean theorem, the length is this. Okay. We call this the modulus. It's really easy to show that if you got two of these things and multiply them, so let's just do that. Okay, so multiply these, you get A1, A2 minus B1, B2 plus A1, B2 plus B1, A2 times Y. Okay, that's just by the distributive law. If you multiply A1 by A2, you get A1, A2. If you multiply A1 by B2I, you get your A1, B2I, which is here. Okay. If you multiply B1I by B2I, you get B1, B2 times I squared. Well, what's I squared? It's -1, because I is the square root of -1. So you get your negative B1, B2, and you also get, I don't think I did it, the B1, A2 here times I, okay? Okay, well, as it turns out, you can do the trigonometry and it's not difficult. If you got, let's say, C1 here and C2 here. And let's just say one is, let's just say this is a unit circle. So Z1's a little bigger than one, Z2's a little less than one. Okay. That probably wasn't a good choice. But I'm going to stick with it. Okay. If I multiply these two, the result, Z1 times Z2. So here's angle theta 1, here's angle theta 2. Okay, Z1, Z2 adds 2 angles. Okay, so this angle is theta 1 plus theta 2. That's the angle all the way around. It's not drawn very well. I could have drawn a much better picture. But your book has a good picture. Okay. So when you multiply two complex numbers, you're just adding their angles. And then you multiply their moduli, their lengths. Okay. Well, this is a little bigger than one. This is a little less than one. So it maybe comes out kind of close to one, but I'll make it a little bigger. Sure, it's not always one. Okay, so the length. Okay. We'll represent the modulus with absolute value signs. And the modulus is just the magnitude of Z1 times the magnitude of Z2. So you just multiply their lengths, add their angles, and you have the picture of the sum of the product. Okay. The sum, you just add them as vectors, head to tail. And you can see that, that's real easy to see. If you add A1 plus B1I to A2 plus B2I, you get A1 plus A2 plus B1 plus B2I. Okay, and you can see how that works out in the plane. Okay. Their book is a little more formal about it, but it's the same what I just said. You want to read the formality. You want to understand the formality because we're going to use the formalities when we talk about complex vector spaces, which are just like any other vector space, except your components can be complex numbers and your scalars are complex. So the multiplication, addition, everything. You got to know that, but that pretty much disposes of section 8.1. There's not much in it, but the whole thing, and they don't even talk about the picture of multiplication. They just talk about the distributive law. Now, they get to De Moivre's theorem, I think, by section 2 or 3. So we'll just look through it. Okay, and division of complex numbers is a little more complicated. No, it can't be obvious. Well, there's division. C1 divided by Z2 is this, right? Well, that's equal to A1 plus B1I over A2 plus B2I multiplied by A2 minus B2I over A2 minus B2I. Okay, because of course this is just 1. Since the numerator and denominator are the same. When you do this, you can check out the distributive law. The denominator becomes A2 squared minus B2 squared. A2 squared plus B2 squared, sorry. Okay? Which is just the square of the modulus of Z2. And your numerator becomes, I don't have room to write it here, so I'm just going to, I won't even attempt to squeeze it in. I'll just write it 2 lines. You get A1, A2 minus plus B1, B2 plus the quantity A1 need to think ahead before I write. Okay, A1 B2I is negative A2 A1 B2 plus A2 B1 I. Okay, in other words, you just rationalize the denominator and you get the quotient. And this equals got something wrong. It should be A1 B2 here. I use norm signs. I should use a single absolute value type sign. You understand what that means? Okay. It follows that this times this equals this. And from that, it follows that when you divide two complex numbers, you divide their magnitudes and you subtract the angles. Just inverse to what you do when you multiply them. Okay, I'm not going to try to illustrate that because we're just about out of time. B bar, which is A minus BI, is a complex conjugate of this. So what we did up here was we knew that multiplying the denominator by the complex conjugate gives us this. Now that's easy to verify. You just multiply this by this. So you multiply complex number by its conjugate, you get the square of its modulus. I didn't write square down here. Do C2 squared. Okay. So that's terminology, and all that's really pretty straightforward. You have the division of complex numbers here. And then you have these formal properties of complex conjugates. So what I'm going to ask you to do, I'm not going to give you a formal assignment on this for this time, but please do thoroughly read the first two sections of the chapter. And the last section doesn't really have a whole lot new except the Mauver's theorem, which I've already, well, I haven't really showed you. You know, what happens if you take the nth power of a complex number? Well, if you took the second power, you'd be adding the angle. You have twice the angle. Because if you got this angle, if z has this angle, then z times z has this angle plus this angle, okay? And its magnitude is just the square of the magnitude of z. So the nth power of z is going to have n times z, which means you might loop around the complex plane a few times for a large power, or a whole lot of times. And that leads to some pretty interesting geometry. So once we get through that, then we're ready to do some linear algebra with complex numbers, okay? So we'll talk about the rest of this next time. I'll ask you to read it, and I'll probably give you some problems to work on over the weekend. Haven't totally settled on what assignment I want to give you this weekend. So for next time, as I say, read, look at the problems at the end. Most of them are straightforward, okay? It wouldn't hurt you to work a few. So do that, because there are going to be a couple of things that you have to do this weekend. So you don't want to sit in your thumbs between now and Thursday. You want to be prepared for everything. Okay, good.